The next speaker of today is Elder Costa, who'll talk about quantum coherence of a uniformly accelerated detector. Elder, you have 20 minutes, including questions, so feel free to use this time. Floor is
Oh, okay. I'd like to thank you for giving me an opportunity to talk at RQI Circuit Online. My name is Elder from POE Brazil. Today, I'm going to talk about quantum coherence of a uniformly accelerated detector. Here's my collaborators, Pedro, Irisma, and Olympio. The purpose of these presentations is to show you the loss of coherence by Unruh effect in the quantum interference. In particular, I will show the behaviors of wave particle properties and the Unruh effect. Okay. Quantum coherence is a fundamental concept in quantum physics. It refers to ability of quantum states to meeting its entanglements and superpositions. However, coherence is a fragile property. It can be easily disturbed by interactions with the environment, for example. This process is known as decoherence. Recently, several papers have studied quantum coherence and relativistic contexts. Let's see a few then here. In particular, in this coherence, in this reference, according to the authors, the Unruh thermal buff causes the coherence and destroying the properties of the uniformly accelerated Unruh-DeWitt detectors. So, in order to investigate the wave particle duality of a uniformly accelerated qubit, we consider the quantum scattering circuits conformly illustrated in theory. Okay, and then quantum scattering circuits involving controlled interactions between a single qubit, the probe qubit, and the system of interests, quantum fields. Here, the coupling between the detector and the quantum fields modify the interference patterns. In this context, the scattering circuit can be used by estimating the Unruh temperature and the loss coherence induced by Unruh thermal wolf. Let's see how its setup works. Suppose initially that systems probe qubits and the plus and the field is prepared in the state given by product state. Okay. And then the action of the first Hadamard gas transforms the qubit states to the superposition states and the superposition states. Okay, the probe qubits is linearly accelerated and coupled to a massless scalar field. This couple is described by U operator. Here, we consider the weak coupling regime, where the U operator given by this expression and the leading order and the first perturbations theory. Okay. In addition, the phase shift is introduced. Okay. See if the qubit is the STED state, okay, and the U operator induced by following transformation in leader order. Okay. Finally, the operations of the Hadamard get the final states of the system region. Okay. And then the reduced dense matrix of the qubits is given by these expressions. Okay. Note that the diagonal terms corresponding the probabilities to measuring the detector and ground states. Okay. Probability given by Pg and the probability Pi. Okay. And then off-diagonal terms encode information about quantum coherence of the system. Okay. So the Franging visibility for interference patterns is defined by difference expressions. Okay. The maximal and the minimal values of the probability Ag occurs when the alpha equals 0 and the alpha equals P. The visibility is given by equations. Okay. And here we plot in the visibility of the qubit as a function of the accelerations. We observe that when the accelerations increases, the visibility decreases monotonically. This indicates that the loss of coherence. In this paper, we find the relations between the Unruh temperature and the visibility. Okay, is given by these equations. Okay, now in order to obtain which way informations, we removing the second Hadamard from the interference setup illustrated provisory, and we including two detectors, detector A and the detector B. Detector A measures the qubit and ground states, while detector B measures qubits and the accepted states. Choose the which way informations can be stored and the internal states of the qubit. So the probability of finding the qubit and the ground states is given by expressions, and then we have the probability of find the qubit and the steady states. Okay. Page informations is quantifying by the difference between the probabilities WA and WB. Okay. This is a normalization factor. By using these expressions, we find these results. Okay. So let's to explore the behaviors of wave particles duality under the Unruh effect. For this, let's to analyze the complementarity relations. The complementarity relations is given by this inequality. Okay, not that the equality is satisfies when both the qubit and the field are in a pure state. Okay. In these figures, we plot the behaviors of visibility, page informations, and the complementarity relations as a functions of the accelerations. It shows that the visibility, page informations, and complementarity relations decreases with increases accelerations. This suggests that in regimes of high accelerations, the Unruh-thermal buff has a some impact on its wave particles properties. For very high accelerations, the complementarity relations, blue plot, indicate a maximally mixed states of a probe qubit. In this case, no information about the wave and the particle aspects the qubit can be obtained. This lack the knowledge about the probe systems is due to another quantum properties, namely quantum entanglement. And in the other words, the qubits and the scalar fields becoming maximal entanglement, and the information about wave particles properties is being shared with the quantum field. Okay, in this other figure, we can see that the visibility and the complementarity decreases as the interactions time grows. In contrast, the page informations approach its maximal value for a long time iterations. Okay. So, all findings suggestions that the creations and the particles by the accelerations serve as the environment of the qubits, leading to a loss information about the wave and the particle aspects of the qubits inside the interferon. So let's me summarize the case points. First, the interference partners is modified by the Unruh effect, and the interference and the Unruh radiations affects the wave particles properties of a uniformly accelerated qubit, and then the Unruh effect disturbs the internal states of the qubit, leading to loss information about the wave particle duality. Thank you for your attention.
Thank you, Elder. Thanks a lot for the talk.